So if you read carefully the title, edging closer to the hardware for kernel CI and input devices, you would get that this talk is also about input, which is boring, I know. But it's also about CI, and I hope that you will get very enthusiastic about it. Why me? Peter made a short introduction of myself, but basically what you have to know is that I'm a kernel developer. I work in the input and the heat stacks. And I'm usually the one that breaks, who breaks your touchpad, your keyboard, or your mouse. So, and that's the input part, of course, of this talk. But now, since 1 year, mostly, I'm the heat co-maintainer in the kernel, which means that I can also block your patch if you send a heat patch, or I can delay it at least. And this is why I had to work on the CI part, because with more responsibilities, then you actually need to make sure that you do not break existing devices. Otherwise, you will come back to the first point where I've broken your touchpad. So I don't know if many of you know about the heat subsystem and the heat input. We made previous presentations, but it's basically a human interface device. It was created in the late 90s. And the idea was that you would be able to plug and play your USB mouse on Windows 95 without having to download a new driver for it. So it was on Windows 95, so USB only. But now with recent development, we've got wireless mice with Bluetooth, Bluetooth low emission, and we even have I2C for laptops for saving powers. So how does it work? It's relatively easy for mouse. You've got one piece in the device that you can query, which is called the Repo Descriptor. The Repo Descriptor just gives you what bits correspond to which event on the report that the mouse will be sending. So for instance, here this mouse will give you an X of 8 bits, Y, the buttons 1, 2, 3, and then you will get 5 bits of padding just to make up to 8 bits. And if you look at the stream of event, you will get 0, 0, 2, and you can easily convert this to X0, Y2. The button 2 is getting held down. Then we continue to hold the button, and then we release the button. So this seems like very simple. The problem is that with Windows 7, Microsoft introduced a multi-touch specification, and it was not very clear on how the event stream would be. It was sort of working, but not quite. So in this very simplified version of the report descriptors, I mean, this won't work, of course, and that's on purpose. You could imagine that you would say, okay, X, Y, the tip switch, which is basically the device is actually touching, the finger is actually touching the screen. And we've got 7 bits of padding, and then we've got a second touch in this one. And if we receive this stream of events, we can detect that, well, the first finger is at position 5, 2, then with 0, and then we start saying, okay, but the second finger and the second line, is that the same one or not? So they added a tracking ID. But then suddenly when we receive nothing, what does that mean? Does that mean that we release the finger? Does that mean that we have still our 2 fingers there, that they have not been updated? It was kind of blurry in the specification. So luckily, with Windows 8, we've got a better specification, but still, we've got a lot of devices who have a different interpretation for this event stream, and which means that whenever we introduce a new patch, we need to ensure that there is no regression in the kernel to not break those particular devices. And so my initial idea was to do manual testing. And if you heard Martin's talk on Wednesday, it's not going to scale, you know it. So at the beginning, my first question was, do I have a lot of multi-touch panels? Yes, I would be able to test it. That doesn't work. But also not that I have mouse to test, I have mice to test. That just doesn't work. So basically, for manual testing, and this is something that you all know, it just doesn't work. It's time-consuming. You're never sure whether or not you're doing full testing. and it's not compatible as long as you start having to pile new patches and everything, and you want to make sure that every single patch does not break anything. So yeah, the answer is no. So the first idea I had back in the days for HID multitouch was to ask people to actually send me recordings of their devices, which for a tool that I wrote in C, which was called HID record. And then I would replay them locally with a tool that I also wrote, which is called HID replay. And then I will compare the difference between the recording of the device and the new one. This was based on a module kernel, on a kernel module level that is called UHID. But it was not working for many reasons. One of them is that it was imprecise. As soon as the machine was on the load, I did not receive the same event stream, so I had to make some approximation. I needed to update the database of the event, the receive event for every kernel, and it takes too much time because I had to replay all of the devices in real time. So if a user gives me a 10-minute record, then I have to spend 10 minutes replaying this particular device, which really doesn't scale. So I had a look at what was around, and Peter made a wonderful presentation previously, and you saw that there is a libinput test suite, and the idea, which is really normal, I would say nowadays, is that for every commit you write a test, and the test has to be simple, and it saves you a ton of time because you know that whenever you're introducing a new feature, you won't break all of the existing code base. The only downside of that is that it's tedious. I know that Peter, whenever we add a new feature, requests the test, and it's, yeah, kind of like the head pointed tag with the crickets. It's kind of hard to write on that, but that's the downside that we have with this. And so, end of 2017, I started working on HID tool, which is a rewrite of my HID replay and HID record tool in Python. And in addition to just the simple tools, I also add a library to parse the report descriptor, and I also add a library to generate the reports based from the descriptors, which means I can now emulate any device based on the report descriptor that I have. I created a full test suite with unit test. So basically, I can inject events and say, OK, is X, Y, is it, do I receive an X, Y from the kernel? And it supports currently the keyboard, some mice, and the multi-touch panels. Same for libinput, it's tedious, but I'm trying to enforce that any new feature added to the HID kernel for fixing one problem is attached to HID tools, so that I can actually run it in the second port in my CI and make sure that I do not break anything when updating a new feature or new functionality or new bug that we found at the kernel level. So now, what about CI? On FreeDesktop, we have GitLab, which is wonderful. And we've got pipelines, and for every commit or merge request, we can run tests. So that seems wonderful to use. And there are also very good benefits for the GitLab FreeDesktop instance, is that we have a lot of runners run by FreeDesktop, so thanks a lot for that. They are powerful, and you can also add your private ones, which is very nice. And it saves a ton of time. However, when I was starting to look into that, I was working with the libinput test suite, and I realized that the Western test suite and the Mesa test suite were having similar issue, and there were a lot of duplicated things across the project in their pipelines. So initially, when you see the CI's pipelines that are created, it's for web application or this kind of stuff where you don't have that many dependencies. And so what you do is you just run the random upstream image. So for instance, Python 3.6. You update the few components that you need. You install the dependencies, so it takes less than 20 seconds, and you just run your test on it. However, for our components in FreeDesktop, this doesn't scale because updating the base image takes minutes or more. And then you want to install dependencies, which can take a little bit more. And so what we do, and in all of the pipeline that I've seen is that we create our base test image. So we take one of the upstream image, we update it, we install the dependency that we want, and then we publish the image on the internal GitLab registry, which means that next time when we run the CI, we can just take this image and compile our script and compile our project and run the test on it. So we basically save all of the time of updating the image and everything. Problem is every single project has its own version of creating the image. Some were running Debian, some were running Fedora, some were running Arch. And in every single project, there was this tiny benefit that you can find. Like one was actually cleaning up all the man pages because you don't really care about the man pages when you're actually using the container in CI. Some were just storing everything. So I ended up writing a new project under the Wayland umbrella, which is called CI templates, that everybody can reuse. It's MIT. And what you can do is you just take this, and these are the 3 use cases that you want and why you would want to use it. So if you want to save time writing pipelines and making sure that it works on all of the major distribution right now, we could have more. If you also have a reproducible environment to fix the bugs that are raised during the CI, so what you can do is you just download the container image and you just rerun it, and you would have the same setup that what you have on GitLab. And also, this is something that libinput is doing, is that you can ensure that you are continuously building on all of the distributions. So basically what libinput does is that every week we update all of the container images, and we try to run and reinstall our software on it. And if there is a breakage, we know before the user gives us the notification that, hey, it doesn't work anymore on Ubuntu or on Fedora, and can you do something about that? So this is for reference. You can look at it later, but the easiest way is to look at the project. But basically, what you have to do is you just include the Wayland CI templates. You include the SHA-1 as a ref because you do not want to. You want to be sure that you are still running on the exact same pipeline every time you run it. So you don't put master as a ref. And you include the template as Arch because I took the Arch one from libinput there. You have a few variables. You can tell which packages that you want to install on your new container. You can run any script. So like, for instance, here it's bash arch install.sh, and you can put arguments to it. And then you put a tag. There is an upstream repo which basically tells you, okay, if libinput/libinput already has this image, just download it, so I don't have to rebuild it every time. So you can always use the image from the upstream repo. And then there is this last tag, which is where to store the image. And then you just add this small piece of job, which is container build here. You extend the container from the templates, and that's it, basically. And what this does is it's actually, for every build that you do, it checks for the tag that you put in Arch tag there. If the image is there, it will just keep the stage. If the image is not here, it will rebuild the whole container from scratch. So there are several benefits from it. You just include it. It's a small patch to do it. So currently, I already mentioned that Mesa is having this libinput Western. All the images are based on upstream. We enforce that we do not want to pull some random image from some random people, even if it's some well-renowned people. We want to use the one from the upstream project. And they are built locally, which means that if there is a CVE in one of any image, you can just click, change the tag, and you rebuild the whole your whole container, and you can fix the the whole CVEs at once. There is a CI of the CI, so every commit on master on CI templates run all of the tests and to ensure that the templates are actually working properly. And we have support for Ubuntu, Fedora, Arch, and Debian. I recently added support for creating ARM64 images. So thanks, Daniel, for creating the virtual machine that allows us to do that. So I know that Eric Arnold is starting to actually have containers for ARM64 that he can run then later on actual ARM64 board for CI testing. And one bit that I'm actually working on is the support of running VM inside the containers, which we can do on free desktop. And this is where I can do kernel hid CI on, well, not on free desktop, but on GitLab at least. And so now, whenever I receive a commit on the patchwork, on the mailing list, or whenever I push a commit, I have a job on GitLab that run my kernel CI with hit tool previously. I'm using the CI templates with QEMU, the whip branch that I was mentioning. And the GitLab.ci is not in the tested tree, so that's why I have to use my own GitLab. I had to play with GitLab. There is a bug that is kind of worrying for me. A lot of people have it, so I want to be able to include GitLab CI from another project, but still run the particular project because I do not want to patch the kernel sources to have it running. I had to play with Docker, Podman, QEMU, Bash, and Kubernetes. Was quite fun. And finally, this is what it looks like. So these are from 3 weeks ago when the tests were all passing. I've got a USB problem right now. So basically, for every patch I receive, I can run a bunch of scripts like check patch, spores, quick build. Then I create a VM, and I run various tests in the VMs, like test suites. I make sure that there is USB devices that pop up. I make sure that I2C devices are popping up and everything. And that's it. Now I'm open for questions, if you have any. That's going to be easy. All right. Well, thanks.